Hello everyone, this is Nash. Today what I want to discuss is the simple harmonic motion in the case of underdamping, the underdamping case. For simple harmonic motion, it's quite simple because it will be experiencing no friction and no resistant force, so the amplitude will always be the same. There's no any loss of mechanical energy. But try to imagine if your object is now submerged in a viscous fluid. When you're moving, you will be experiencing the resistant force. And the resistant force is proportional to your velocity. Just like you are running, the faster you run, the higher the resistant force will be. So I can fairly say when an object is now moving in a viscous fluid, if it is now moving to the right, you'll be experiencing an opposite resistant force caused by the viscous fluid and the spring force caused by the spring. So how to start all of this is by using the Newtonian mechanics. F equals ma. F equals ma tells you that the total force acting on the object is equal to mass times the acceleration. And now the total force is not only the spring force, but also the resistant force caused by the viscous fluid. So the ma is equal to minus kx and minus bv. The b is some kind of damping constant. All right, and move these two terms to the left, you get a differential equation. So the most complicated part is how to solve this differential equation. That is a question. So what you saw right now, we got three variables like the mass and b and k. So in order to simplify all this term, I'll just simply let the beta equal b over 2m and omega naught is the square root of k over m. This is what you are familiar with when you were learning the simple harmonic motion. All right, just plug them in, you will get a new differential equations. Now they only got two variables. Things are becoming much more easier to deal with this differential equation. If you are experienced, if you're familiar with this equation, you might be able to write down the final possible solutions. But if you're not, maybe you can start from guessing the possible solutions. Usually I'll guess the possible solutions as the x as a function of time, that is a times e to the alpha t. This is some kind of exponential function. Why? Because the exponential function with the base e is quite useful. Why? It's a amazing existence because every time when you try to take the derivative of the exponential function with the base e, it still becomes itself. No matter how many times you try to take the derivative of the e to the power of x, it is still the e to the power of x. So if I want to fulfill this differential equation, I need to find an x, and no matter how much times I try to take the derivative of it, they will still look the same. They will still look just similar like each other. So they will get great chance to cancel with each other. So it's fair to guess the x as a function of time as some kind of exponential function. I hope you can accept this idea. All right. If you can accept this, okay, you can just plug in the x as a function of time back into this differential equation and try to take the first order and second order derivative, or you can plug it in directly and see what will happen. If you try to plug them in, you can take the similar term, the same term right in front, like the a e alpha t, and what you're left with inside this column is actually a quadratic equation with one variable. In my mother tongue, it's called 一元二次方程式. Then you can start using the formula you learned when you were junior high school students. Simply by using this formula, you get two possible alpha. Two possible alpha. Alpha is a constant. Now I know I get two possible alpha, like alpha 1 and alpha 2. So the solution is not that easy. The solutions can be written down as the a1 times c alpha 1t plus a2 times c alpha 2t, right? Since this is the possible solutions, okay, I got the alpha 1 and alpha 2 is minus beta. They'll get the minus beta plus and minus the square root term. Just plug them in this equation, in this solution, the x of t is equal to all of this term, All right, here's the interesting part. If there's no viscous fluid, that means there's no resistant force, there's no damping constant, and there's no damping parameter. If there's no damping parameter, then you are no longer an underdamping case. Then you would just become a simple harmonic motion. So this, you can take this as a kind of homework. What if beta is now equal to 0? Then you will see your x as a function of time is just like a simple harmonic solution. Some kind of fixed amplitude and times a cosine or sine function with some initial phase angle. But what if your beta is not 0? However, your beta is less than omega naught. Then the beta squared minus omega naught squared would be less than 1. If it is less than 1, the square root of minus 1 is actually I. You need to remind yourself, all right, if you keep simplifying this equation, the x of t, they'll get the e minus beta t, and you can simplify the square root term as I omega 1t and minus I omega 1t. And there's a useful tool called the EI theta is equal to cosine theta plus I sine of theta. So you can take your I omega 1t as I theta, and this is minus I theta. And if you put a minus right in front of the I theta, it will be cosine of theta and minus I sine of theta. You can do this in your mind. This is cosine and plus I sine. This is cosine minus I sine. So the first term is the A1 plus A2 times omega 1t. And the second term is the A1 minus A2 times sine omega 1t. Here's the interesting part. In order to simplify this, I'll just name the A1 plus A2 as a big constant, as a capital letter C. And this is some kind of capital letter D. You can square them, take them out, and add them all together, and take a square root of all this term, like the square root of c squared plus d squared. And inside, it will be a c divided by the square root term, and d divided by the square root term. And according to the Pythagoras theorem, I can know that this term could be some kind of sine function or cosine function. It depends. It depends on you. I would like to name the first term as a cosine function, like cosine of theta, and the other term should be the sine of theta. So this is cosine theta times cosine omega 1t and plus cosine sine of theta and sine omega 1t. It can be realized the cosine, the alpha plus beta is equal to cosine alpha, cosine beta, and minus sine alpha and sine beta. This is the same situation for this. So I can simplify all this term as cosine omega 1t minus theta. But since this is just like a initial phase angle, so I would like to use the plus symbol, so I can say the minus theta is equal to some kind of positive sign. I think it's okay. So I write down this equation as a times e to the minus beta t and times cosine omega 1t plus phi. All right, how to realize the final solution? This is the final solution. It's done. How to realize the final solution? For simple harmonic motion, the amplitude is always the same. There's no loss of mechanical energy. But for underdamping case, you are oscillating inside a viscous fluid. You're always losing the mechanical energy once if you are oscillating. So you can imagine that the amplitude would drop. It will decrease as time goes by. You are still oscillating, but your amplitude is decreasing. So the a times e to the minus beta t is actually the amplitude as a function of time. And you can imagine it will keep decreasing as time goes by, because the e to the minus beta t can be realized as 1 divided by e to the beta t. As t increases, the denominator increase, and the whole term decrease. So your amplitude will decrease as time goes by. But you're still oscillating because you get a cosine function. It still oscillates as a cosine function. This is your oscillatory term. So if you try to plot this solution as a diagram, the vertical axis is the amplitude as a function of time, and the x-axis is the time. And you will see your amplitude is dropping, is decreasing as time goes by, but however, you're still oscillating as a cosine function if the phi is 0. Let's make it simpler. So this is how we deal with this simple harmonic motion in a special case called underdamping case. Your object is now submerged in the viscous fluid. You're experiencing a resistant force every time you're trying to oscillate. The spring force is no longer the only force, but there's a resistant force proportional to your velocity, and it's always pointing to the opposite direction with the velocity you are moving. All right, I hope it's helpful, because when I was a college student, the first time when I learned this chapter, the textbook only taught me that the final solution, but they never really tried to tell you how to derive all these equations. So today, I hope I can fulfill your curiosity. All right, thanks for watching, and this is Nash.